Why didn't the two parallel lines recognize each other? Because they had never met. And so we're going to show that some lines are parallel and never meet using angle relationships. Before, we had two lines were parallel and we could tell you about the angles that were created by those parallel lines and transversals. Now, we're going to look at special angle pairs that are either congruent or supplementary and use the converse of the theorems and postulates, so the switch, to show that the lines are actually parallel. So proving lines parallel, if certain angle pairs are congruent, then the two lines crossed by the transversal must be parallel. So some of the congruent angles we'll deal with are corresponding angles. And that, if I have corresponding angles here in this picture, if I can show any two corresponding angles are congruent, then I can show the lines are parallel. This is called the converse of corresponding angles postulate. So let me just go ahead and fill in some corresponding angles for A. So if I could show that A and E were congruent, or if I showed that B and F are congruent, or C and G, or D and H, any one of those pairs would be sufficient to show that lines M and N are parallel. Don't forget always that you need to know which is your transversal. In this case, since I was trying to show M and N parallel, the line P is a transversal. All right, now another set of congruent angles are the alternate interior angles. So we're still dealing with the same transversal, which is line P, and we're going to show that lines M and N are congruent using the converse of the alternate interior angles theorem. So that means for angle C, its angle pair is E. For angle D, its angle pair is F. So if I show either one of those being congruent, then the lines have to be parallel. The last set of congruent angles are the alternate exterior angles. Again, here's my transversal, line P. So we're showing lines M and N are parallel. And I'm using the converse of the alternate exterior angles theorem. So if I show angle A and angle G are congruent, or if I show angle B and angle H are congruent, that is sufficient to show that the lines are parallel. So let's just do a very quick and short example. I want to show that R is parallel to S given that angle 4 and angle 8 are congruent. When you have a given in a proof, that is assumed to be true. So first thing you normally do is write down the givens. Angle 4 is congruent to angle 8, and that is true because it's given. So I go ahead and take a look at angle 4 and angle 8 here, and one thing you can see is that they are alternate exterior angles. So if those are congruent, then R has to be parallel to S, and that is using the converse of the alternate exterior angle theorem. You can see how I shorten it up. CONV is converse, ALT is alternate, EXT is external, and there's the angle symbol, and then theorem. Now, there's another way to prove that lines are parallel is when certain angle pairs are supplementary. So one of the angle pairs is same side exterior angles. You can see here if I show that those add up to 180, remember the definition of supplementary is that they add to 180. So if angle D and angle E add up to 180, that's enough to show that lines M and N are parallel. So again, I'm just going to highlight the transversal right here. And that can change based on the problem. If I had angle C, that goes with angle F. So if I show those two add up to 180, then that is sufficient to show that M and N are parallel. Again, the name of this theorem, it's just like the other theorem, except it has converse in front of it, because we are switching it around. Instead of saying, if the lines are parallel, these angles are supplementary, now we're saying, if the angles are supplementary, then these lines are parallel. The other set of same-side exterior angles are same-side exterior angles. So you can see angle A over here, And so if I go same side exterior, the angle that goes with it is angle H. If I use angle B, then I get angle G. I just have to show that those two angles add up to 180 degrees, and then use the converse of the same side exterior angle theorem. In this proof, basically you have proved that L is parallel to M, given that P is parallel to R, and angle 1 and angle 3 are congruent. So the first part I have is the given. Line P is congruent to line R. Then in step 2, I say that angle 3 and angle 2 are congruent. Well, you can see right here, angle 3 and angle 2 are congruent. If the transversal is M, those are alternate exterior lines. And I can assume that they are congruent because they are alternate exterior angles, which is the purple up here. Then the next thing I have is angle 1 is congruent to angle 3. Well, how do I know that? Well, it's in the given, so that's automatically assumed to be true. Can I assume then, if angle 1 and angle 3 are congruent, and angle 2 and angle 3 are congruent, doesn't that mean then that angle 1 and angle 2 have to be congruent? Yes. It's kind of a switching. You see how I replace? You could either call it substitution or the transitive property of congruence, and you can see that angle 1 is congruent to angle 2. Finally, that means that line M, let me go ahead and change my ink color here. So my new transversal, if I'm trying to show L is congruent to M, there's my new transversal. I showed that this angle 1 is congruent to angle 2. Well, those are corresponding angles for this purple transversal. So if the corresponding angles are congruent, then the lines have to be parallel. That's by the converse of the corresponding angle postulate. Now we also have one extra theorem. It's actually in the next section, 3-4, which we partially covered already. And it says if a transversal is perpendicular to one of two parallel lines, then it is perpendicular to the other line. So if R is parallel to S and T is perpendicular to R, then that tells you that T is perpendicular to S. So using this postulate, what we're going to do is we're going to prove that BC is perpendicular to CD. We know that AB and BC are perpendicular, so you can see here's my transversal. And we also know that angle 1 plus angle 2 equals 180. I do not know that the lines are parallel yet. So first of all, let's go ahead and see. AB and BC are perpendicular. That's part of the given. And the measure of angle 1 plus the measure of angle 2 is 180, also part of the given. Now we say angle 1 and angle 2 are supplementary. That is by the definition of supplementary angles. In other words, two angles that add to 180, that is supplementary. Now here I'm missing the statement side. Usually this first part is called the statement, and the other part, the second part, is called the reason. Here I need to fill in the statement. You can see that the reason is a converse of same side interior angle theorems. So the only same side interior angles I have are angle 1 and angle 2. That's actually for, here, let me erase this. That's actually for a different transversal, which is why I'm actually changing the colors on these. So if we go, let me go ahead and see angle 1 and angle 2. So we learned that those are supplementary. Well, they are same side interior angles for this transversal AC. So I can say then that AB is parallel to CD by this converse of the same side interior angle theorem. Well, if I know AB is parallel to CD, then that means that this angle here, let me go ahead with a different ink color, this angle has to be 90 degrees by the perpendicular transversal theorem. If you have two parallel lines and one of them makes a 90-degree angle with the transversal, then the other one makes a 90-degree angle with the transversal. So in summary, to prove that lines are parallel, write down your givens, do a drawing, label anything you need to label. Look for special angle pairs. For the congruent angles, that would be corresponding, alternate interior, or alternate exterior. Or maybe it's supplementary angle pairs, which are same side interior or same side exterior. You may need to use a definition of supplementary angles like we did in the last proof. Then finally, once you identify your angle pairs and show that they are behaving the way they're supposed to, you can use the converse of the appropriate postulate or theorem. So to reflect, why do the theorems proving lines parallel have the word converse in their name? Well, I'll give you a little hint here. Let's take the corresponding angles one. If two lines are parallel, then the corresponding angles are congruent. Now I'm trying to prove the lines are parallel, so I'm going to switch the two and say if two corresponding angles are congruent, then the two lines are parallel. So hopefully that was enough of a hint.